Hello class, this is my extra credit video on how to do advanced stoichiometry equations, specifically ones where we're trying to find the concentration of all ions present in a formula. So let's get started. If you hear any bells ringing in the back, it's because my cat's probably going insane. Yeah, there she is. So let's get started. So what I have here is something I kind of wrote out just for myself to study. It's kind of a step-by-step deal to kind of help you go through this problem a little easier, more fluidly. I'm trying to get faster at these, so come test day, I'm not going to be stuck for 30 minutes to an hour trying to figure it out. So I've just been trying to study this and get it down. If any of you would like this, just let me know on the Teams app, and I'll be sure to send it to you. So here's our question. This is a question I found online. I kind of switched it around a little bit to make it, helpful to use in our class. I even included density in there to, give us some density help too. Anyways, so I went ahead and wrote down what we want. We want the concentration of all ions that remain after the reaction. See that here? We're given 1.5 grams of lead-2 nitrate. 0.5 grams, this is lead-2 nitrate. And then we're also given, change this to liters, 0.125 liters of a 0.100 m sodium sulfate solution. So that's going to be here. I wrote that down. And then we're given the density. It's 4.53 grams per milliliter. Okay. So then we went ahead and wrote our formula, and we determined this was strong, this is strong, this is weak, this is strong. And if you want help with that, determining if it's strong or weak, we can go here to our cheat sheet. NO3. NO3, strong. Only exception is Ag. NO2, and that's for the here, not 3. We're correct there. This is strong. So Na2SO4, strong, no common exceptions. And then I think we even have SO4 here. So if you want to check again, yeah, strong. We're not in there. And then PbSO4, go to SO4, Pb, weak. Okay, and then strong. So that's strong because Na, no common exceptions. So we want the concentration of all these ions. So Pb 2 plus, NO3 minus, Na plus, and SO4 2 minus. So what we're left over with is PbSO4. It's weak, it doesn't break up. This is our, my little beaker. PbSO4 does not break up. We have Na, NO3. Those do break up. So Na plus into NO3. So we have NO3 here. It's going to be here. And then Na plus, plus. And then what about these two? Well, you might think it's right there, but it isn't, because this is one compound. This is completely different from what these two things are. So you would think it'd be 0, right? The concentration after. But if we have a certain, if we have an ion that remains, our excess reactant is going to be able to tell us which one of these is going to be 0 and which one's going to actually have left over. So we're going to want the volume of our full solution. It's going to help us later in the future. So we're given this, and we don't know the volume of lead. So we're going to use density equals mass over volume. We want volume, right? So we're going to go times V, get it on this side, divided by density. So then V equals M over density. Okay, So we have mass and we have density. So our mass is going to be this in grams. Our density is 4.53 grams per milliliter. Let's go ahead and do that here. There's our answer. So we got 3 sig figs here. Let's go ahead and do that. 3, 3, 1. So these cancel. Milliliters. And then we're going to want this in liters because that's what this is. So let's go ahead and add. Let's do this. So we're going to go. One thing I forgot, we got to write our stoic map for this. So mass of PbNO3 over volume of it no, not the volume, density. That's why you always write these first. I messed up here. Gonna give us the volume. This is gonna be grams. This is gonna be grams per milliliter. So that's gonna give us this. We already did the work down here. So now we're gonna go from milliliters to liters. Oh, our map. This is okay. $1,000 milliliters in 1 liter. It's gonna give us 0.000331 liters, which we can say this is 3.31 times 10 to the negative 4 liters PbNO3. Okay, so now we can go ahead and add this to our given. It's going to give us a total volume 5,331 liters. Let's put that in 0.125 liters for sig figs. Okay, so that's our total volume. And we got that by doing volume of PbNO3 plus volume of Na2SO4. That gave us total volume. Okay. Now, how many moles of sodium sulfate we have? Okay, so to do this, you just look at my whiteboard. Equals mole solute V over solution. So we're looking for this, so we just M times V equals mole solute. So we're going to go to the moles of that. Okay, I'm going to go Oh, I got that flipped around. It's okay. And let's see what we get. Get 0.01, and then let's go 3 for sig figs. That's going to give us moles of Na2 SO4. Awesome. So this is something we should have done earlier, actually. But let's go ahead and do it now. This is a solid. These are strong. Okay, let's break these up into their separate ions. Pb plus 2. Plus. Okay, yields. This is weak, stays together. Oh, I'm sorry, I don't know why I did that. Okay, so let's go ahead and cancel. This is NO3 actually, sorry. Okay, so we're left with Pb plus 2 plus SO4 yields. Awesome. This is our net ionic equation. And I believe it's balanced. 1 Pb, SO4. Yep, balanced. So since we know from Na2SO4, all the sodium from this, all the sodium from this went straight to this. So what that means is all the sodium that we had is going to be what's left over, right? So it's going to be left floating around in our beaker. So we're going to go from moles, let's go moles Na2SO4. We're going to go to, we want to know the moles of Na that was present in this reaction. So we're going to go 0.013 2SO4 moles of Na2SO4 and moles of Na. Okay, so we know for every one of these, we're going to get 2 of these. So that's just going to be, I can do that off my head. Just cancel. Be left with moles of Na. No, not Na, Na. Perfect. So since we know all the Na came from here, that means on this side, all this Na right here is going to be the same amount of moles that was on this side. So since one of our, one of the things we're looking for is a concentration of Na+, what we can go ahead and do is from the moles of Na, we can find the concentration. So we know the volume of our total solution already, and we know the moles of the solute. So that's going to give us the molarity of Na. So we're going to go moles of Na over volume solution, and that's going to give us molarity of Na. It's going to be Na plus, right? All right. So we got 0.026 moles. Then our volume is this. That I cannot do off my head. What's that? Perfect. Go back here. Establish this one. It's going to be the same here. So, awesome. So now we need to find this guy. So what we're going to go ahead and do to find NO3 minus, we know that all the NO3 here, all of it here, right? So we can find the moles of lead nitrate. We're going to convert to the moles of nitrate, and then from the moles of nitrate, we're going to be able to find the molarity of nitrate. So let's go ahead and we're going to go grams PbNO3. We're going to go to moles of PbNO3. And then for moles of that, let's just stop right here, make it simple. Moles of NO3. Okay? So we have 1.50 grams PbNO3. And multiply that by grams PbNO3 to mole PbNO3. Let me go ahead and pull out my periodic table here so we can determine the grams per moles, or the molar mass, the correct term. I'm going to go ahead and find Pb, and its mass is 207.2. Okay, and then N is 14.0067. And then 3 oxygens. So I'm going to go ahead and put this in parentheses, 15.9994. And then we have 3 of those. Close the parentheses. That is our deal. Okay, so we're going to go 1.50 divided by that number. And we're going to get our moles, 0.005. Of PbNO3. Right. So now we need the moles of NO3. So 0.00557 moles PbNO3. Please forgive my terrible handwriting. Nothing you can say will change it. So we know for every one of these, we're going to have 2 of these. That means 1, 2 to 1. So we're going to go 0.00557 times 2. That's going to give us the moles of NO3. Now from the moles of NO3, we can find the molarity of NO3 because we have the volume of our total solution. So what we're going to go ahead and do is mole NO3 over volume solution. It's going to give us the M NO3. Go point. Sorry if y'all can't see that. 0.1114 moles of NO3. Sorry if I start whispering. You can't really hear what I'm saying. When I'm doing math, kind of getting, tunnel vision. Hard to do two things at once for me. Anyway, that's our total volume of the solution. And that's going to give us our molarity. Awesome. So 0.08912 M NO3. So awesome. So now we have these two more to go. So we got to determine which one is the limiting of these two. So PB and SO4, if let's say this one was a limiting, though there's no SO4 that's going to be alone as an ion, if it's limiting, all of it was used up. So that means that one's going to be 0. If it's excess, the remaining moles of it will tell us how much molarity or concentration of it is in our solution, because not all of it was used up. This is why Stoic maps are awesome. So the mole of PbNO3 we already found. So let's just write this down over here. Make it a little cleaner. And we also found the moles of Na2SO4. So point. So we got to determine which one of these is our LR. So to do that, we're just gonna pick, say, this guy. That's gonna be the guy we use. So this equation's pretty simple. Everything's 1 and 1 here. Oh, except him. But I'm gonna use him because it's easier. So we have 0.00, sorry, let's draw our Stoic map. We're gonna go from moles of PbNO3, and we're gonna produce moles of PbSO4. So 0.0057 mole PbNO3 times, and then we use this for our ratio, PbNO3, the moles of that, 1 mole to PbSO4, and it's 1 and 1, so 0.0057 moles of PbSO4. These are 1 and 1, so I mean you can see that this one's definitely going to be a LR, but let's work it out so we can prove that. We're going to go from moles of Na2SO4. We want it in moles of PbSO4. Okay, so we're going to go 0.13 mole Na2 SO4 times 1 mole PbSO4 to 1 mole Na2SO4. And that will tell us 0.13 moles of PbSO4. So this is our LR. So since it's our LR, all the SO4, I mean all the Pb was sorry. All the Pb, since this is our LR, all this Pb was used up in our reaction. So that means we have a concentration of 0 left over. SO4 is our excess. So let's determine how much is left over of this guy. So what we're gonna do is use the LR to see how much of the ER was used. So we're gonna go from moles of PbNO3 to moles of Na2SO4. Okay. So you got 0.0057 mole PbNO3. We're gonna go to sorry. So these are 101 also. Let's cancel, right? This 0.0057 moles of PbNO3 used. And we started with this many moles of PbNO3. I mean, oh, I'm sorry. What am I doing? Na2SO4. That's how much Na2SO4 was used in our reaction. So we started with 0.13 moles of Na2SO4, and we use 0.0057 moles of Na2SO4. So that means what remains floating around in solution, 0.13, 0.0057, 0.1243 moles of Na2SO4 remains in our solution. So with this number, now we can find the moles of what we're looking for, SO4. So we're gonna go from moles of Na2SO4, and we want it in moles of SO4, right? So we're gonna go 0.1243 moles Na2SO4. And then so moles of Na2SO4 to moles of SO4. And we can see for every 1 mole of this guy, we're gonna have 1 mole of this guy too, right? Because SO4, we only have 1 SO4 in here. Yep. That's gonna be 101 again. Oh, that made life really easy. I didn't think it was gonna work out like that. 1, 2, 4, 3. Moles of SO4. Okay, so now we can find the concentration of SO4. So we're gonna go mole SO4 over volume solution And that will give us the concentration of SO4. Let's go ahead and do that. 0.1243 over mole SO4. And we know our total again. So we have a concentration of 0.994. And that's SO4. Means we found everything we're looking for. Just like that. Let me know if y'all have any questions, and please let me know if I did anything wrong. Thank you.